In all the videos we've had so far in this chapter, we've talked about the second question of our goals. How does the body maintain a constant pH, particularly in blood at pH 7.4? The answer, of course, was with buffers, and in particular with the bicarbonate carbonic acid open buffer system. So we're really done with that, but there's another really important question that we need to ask, and it's a skill that I want to teach you, and we're going to use it all semester long, and it's highly related. It's the first question. How do you predict when a molecule is protonated or not? That's a critical issue. I showed you the example of aspirin and lidocaine earlier as drugs that would behave differently in the body depending on whether they're protonated or not. And we'll come back to examples like that. Let's move on to our notes and go back to this page right here where we talked about the carbonic acid bicarbonate buffer system. I'm going to use this as another example, or an example again, for this other question we have because we're familiar with it. Let's review the following items. We said that carbonic acid can be deprotonated to become bicarbonate and then carbonate. And the titration curve shows those three structures, A, B, and C, at low, medium, and high pH. That's one of the great things about titrations is they tell us where each structure exists. We also said that at pH 7.4, we tried this out. We said what two structures exist? And we decided because we're here almost to the end of the first equivalent, we have eliminated a lot of A, made it into B, but we have a mixture of A and B. And there's really no C because that doesn't come until after you get into the second equivalency. So that's a really important point. And it gets to the point of, is this molecule protonated or not? Is it protonated as an acid or is it deprotonated as bicarbonate? I also asked you, which of those two is there more of? And we talked about how because we're closer to B, that means we've converted more of A to B, and therefore there must be more B. But now my question is, how much more? Can we be quantitative about this? Can we say, what is the ratio of B to A exactly? Instead of just more, what if we want to know it exactly? Well, that's where we go to use the Henderson Hasselbach equation. So it's very simple. It's on the next page. And you don't need to memorize this equation. It will always be provided for you. But let's take a look at it and pick it apart. There's a pH. That's a variable, and it can be high, low, or medium. We know that. And water can go from 0 to 14. There's the pKa of the molecule we're interested in, or the functional group, the acidic functional group that we want to talk about. In this case, we're interested in carbonic acid and bicarbonate. And then there's the base form concentration and the acid form concentration. So, like I said, what if we wanted to know the base to acid ratio of bicarbonate, the base, to carbonic acid? We would have to know the pH and we'd have to know the pKa. So let's do the Henderson Hasselbach. The pH is 7.4. It could be anything, but in blood it's 7.4. The pKa is 6.3. That will always be the case for carbonic acid because it's a constant. It's like saying, what's the melting point of water? It's always 0 degrees Celsius. Then we can put in the log. And instead of doing base to acid ratio, I'm just going to put R for ratio. And at this point, we can solve for R. We'll subtract 6.3 from both sides. We end up with 1.1 equals log of R. And let's pause the video and have you try. Get out your calculator, see if you can figure out what R is. It's going to require you to get rid of the log term. Do you know how to do that? See if you can sort it out on your calculator. If not, come back and we'll show you how to do it. Okay. The way we get rid of logs is by inverse log. And if you look on your calculator, you probably have a log key. Then look at right above it on the shift, it should be inverse log, which is 10 to the x. What that means is we can take each side into the power of 10, like that. And when you do that, the 10 power, 10x and log go away and you're left just with r. So what we end up with is 10 to the 1.1 power, and the ratio is equal to 12.6. Now, 12.6 is the answer your calculator gives you, but keep in mind that it's a ratio. 12.6 ratio of bicarbonate base to carbonic acid. Now, that is what we calculate. Sometimes I come up with a different number because some books use different pKa's. Some say 6.1. We're going to use 6.3, and it should be about 13 to 1 here. Sometimes I calculate out to be about 20 to 1. Nonetheless, it's more than 10 to 1 of the bicarb to carbonic acid. Now that's Henderson Hasselbach is going to be extremely useful for us for doing what we just said, calculating the base to acid ratio. We can also do it for other things, like if we know the base to acid ratio and we know the pH, we can actually calculate the pKa. Or if we know the base to acid ratio, we know the pKa, we can determine the pKa that, rather the pH that is needed to generate that base to acid ratio. So we'll practice all of these mathematical manipulations, but it's a really important equation because it really works. And it governs the ratio of base to acid and how it's related to pH, which is extremely important. So that's Henderson Hasselbach, and we'll practice that skill out mathematically on the homework a little bit.